Silicon dioxide, commonly known as quartz, is an important mineral with numerous uses. It is used as oscillators in watches, radios, and pressure gauges. It is used in semiconductors in computers. It is also essential to the gem trade. It is used as a gemstone. Today's discussion is about packing efficiency. Packing efficiency is the percentage of total space filled by constant particles in a unit cell. Here there is a unit cell. You can see particles at the corners as well as at the center of all the faces. And if you look at this figure closely, you can see spaces in between the closed packing known as voids. Last class we learnt about voids in detail. Now we are going to calculate the packing efficiency or the percentage of total space filled by the constant particles in a unit cell. Let us first calculate the packing efficiency in face-centered unit cells. As we had discussed earlier, the HCP and CCP closed packings have face-centered unit cells. That is, constant particles are at the corners as well as at the center of all the faces. For convenience, we have taken only a single face A, B, C, D and the particles at the corners A and C, and the center of the face is filled by another particle. Now, how to calculate the packing efficiency? The formula is volume occupied by particles divided by total volume of unit cell into 100. That is, we are calculating it in percentage. Now look at this figure again. We have the face ABCD. Let's take the side of the unit cell as A. All these sides will be equal because this is a cubic unit cell. So all the sides AB, BC, CD, AD, all these sides are equal to A. And let us take R as the radius of the hard spheres. We have taken the constant particles as hard spheres. So A is the side of the unit cell and R is the radius of the particle, constant particle. Now consider the triangle ADC. AC is the face diagonal and we have a right triangle ADC. Since it is a right triangle, we may apply the Pythagoras theorem here. So there is a triangle ADC and it is a right triangle. So the hypotenuse square, that is AC square, is equal to the sum of the squares of the sides AD and DC. Now what are AD and DC? They are sides of the cubic unit cell. Hence we can put it as A square plus A square, and AC is marked as B. So B square is equal to 2A square. B square is equal to 2A square. And if you consider the constant particles at the corner A and C and the center of the face ABCD, you may see that it is equal to 4R. 4R. So B is equal to 4R because the particle at the center, its diameter is 2R, and the radius of two spheres, the one at the corner A and the one at the corner C, their radius is also included in the face diagonal AC. So total you get B is equal to 4R. Now you have two relationships. B square is equal to 2A square. B is equal to 4R. That is, from this you have B is equal to root 2A. Now we can equate the right sides of these two relationships. Root 2A is equal to 4R. So A is equal to 4 by root 2R. That is equal to 2 root 2R. That is, A is equal to 2 root 2R. Now we have a relationship between the edge length A and the radius of the sphere R. A is equal to 2 root 2R. Now let's calculate the volume of the particles. Since this is a face-centered unit cell, the total number of particles in a face-centered unit cell is equal to 4. Then what about the volume of a constant particle? Since we have considered the constant particles as hard spheres, the sphere has volume 4 by 3 pi r cube, where r is the radius of the sphere. So 4 particles are there, effective number 4. So 4 into 4 by 3 pi r cube is the volume of particles. Now, what about the volume of the unit cell? The unit cell is cubic and side is A. Volume of the unit cell is A cube. So we have the volume of particles as well as the volume of the unit cell. We had already derived the relationship between A and R. A is equal to 2 root 2R. Keep this in mind. Let us recollect the formula for calculating the packing efficiency. It was the volume of the particles divided by total volume of the unit cell into 100. Now we have already calculated the volume of the particles, 4 into 4 by 3 pi r cube, and volume of the unit cell A cube, but instead of A we are going to write it as 2 root 2 r. A is equal to 2 root 2 r the whole cube into 100. So this is how we are calculating the packing efficiency. So I am marking packing efficiency as PE. PE is equal to 4 into 4 by 3 pi r cube divided by 2 root 2 r the whole cube. That is the volume of the unit cell. So if we expand it, we get it as 4 into 4 by 3 pi r cube divided by 2 cube into root 2 cube into r cube into 100. So this r cube and r cube gets cancelled. Applying the value of pi 3.14, we get it as 74%. So the packing efficiency of hexagonal close packing and cubic close packing with face-centered unit cell is equal to 74%. Now let's calculate the packing efficiency of a body-centered cubic structure. So this is a body-centered cubic structure. A similar unit cell, a cubical unit cell can be seen, but the particles are placed in a different manner. In the body-centered unit cell, you can see particles at the corners, and there is a particle at the body center. So look at this body diagonal AF. There is a body diagonal AF. It is marked as C. So at the center of the body there is a particle, and we have particles at the corners A and F, which is clearly shown in this unit cell. So we are going to take that particular body diagonal and the constant particles along that body diagonal for our calculation of packing efficiency. So let us take the triangle ADF. It is a right triangle. Angle ADF is equal to 90 degrees. And the side AF, which is the hypotenuse, it is marked as C. And the face diagonal DF is marked as B. And the side AD is a side of the unit cell which is A. So AF, the body diagonal, and also the hypotenuse is C. The face diagonal DF is marked as B, and the side AD, which is the side of the unit cell, is marked as A. Now in the earlier calculation, we had already found out the relationship between the face diagonal DF and the side A. So if we consider the triangle DFE, you may get B square as 2A square. We had already done this when we calculate the packing efficiency of the face-centered unit cell. Now we are bothered about the triangle ADF and the hypotenuse AF. So according to Pythagoras theorem, for the triangle ADF, the hypotenuse C square is equal to the sum of the squares of the sides AD. AD is A square, plus DF. DF is B. So B square. And what is B square? It is 2A square. So C square is equal to A square plus 2A square, that is equal to 3A square. So C square is equal to 3A square. Hence C is equal to root 3A. Root 3A. Now from the diagram, you look at the diagram and the body diagonal AF or C. C can be written as 4R from the radius of the three spheres touching each other along the body diagonal. So we have two equations. C is equal to 3A and C is equal to 4R. We can equate the right hand sides. So root 3A is equal to 4R. Root 3A is equal to 4R. Hence, A is equal to 4 by root 3R. So in the case of body-centered unit cell, the edge length A is equal to 4 by root 3 R. So keep this in mind. Now we'll calculate the packing efficiency of this body-centered unit cell. We had already calculated and found out that the effective number of particles in a body-centered unit cell is 2. So first step in calculating the packing efficiency is finding the volume of the unit cell. So the effective number is 2 into volume of the sphere is 4 by 3 pi r cube divided by A cube is the volume of the unit cell, but instead of A we are substituting 4 by root 3. 4 by root 3 r, the whole cube into 100. So this is the equation. On substituting the value of pi and cutting r cube and r cube from the numerator and denominator, you get the final value as 68%. We calculated the packing efficiency of face-centered unit cell and body-centered unit cell. Now we are going to find the packing efficiency of a simple cubic unit cell. The diagram is given here. You can see a red cube and the particles at the corners are shown here. As you very well know, in a simple cube, only the corners are occupied by constituent particles. So A and H are the corners we are going to deal with now. So you can see the particles shaded in yellow. As you can see from the figure, the particles are touching each other. So this distance AH, it is equal to the edge length A, because it is one of the sides of the unit cell, and that is also equal to 2r, where r is the radius of the constituent particle. You can view it from the figure. So A equal to 2r. There is no need to consider any triangle here. So it's very clear from the figure itself, A is equal to 2r. Now we can substitute this relation A equal to 2r in the packing efficiency equation. Packing efficiency PE is equal to number of particles in the simple cubic unit cell is only 1. So 1 into 4 by 3 pi r cube divided by A cube. A equal to 2r. So 2r the whole cube into 100. So it comes about 52.36%. So now we have calculated the packing efficiency of FCC, body centered, and the simple cubic unit cell. So FCC 74%, BCC 68%, and simple cube 52.36%. So these are the packing efficiencies respectively. So hope you understood this class. Have a nice day. Thank you.